So I think it's great that Joey is able to join the meeting. I think her own experience and background would also bring in lots of useful elements to the discussions. And at the same time, I can also learn some of the discussion that you guys have through Joey. So meanwhile, I'd know Terry and Ellen would like to hear some of the experience that we have on modeling fish growth under climate change as part of some of the broader modeling work on assessing how climate change affects marine biodiversity and fisheries. So that will be the focus of the presentation. So I won't bore you with all this background, but just quickly, we know the ocean is changing, and today the presentation will focus on mainly two aspects of ocean changes, ocean warming and decrease in ocean oxygen in the 21st century. These are projections by the global Earth system models under two contrasting scenarios, business as usual as shown in red, and the strong mitigation, low emission scenario in blue. Much of the simulation work that I showed, if I don't mention it, refers to the business as usual scenario, which is the red line. And I'm sure it's highlighted in the discussions that some of the starting point of this discussion is that in the wild we notice latitudinal gradients of body size for species such as Atlantic cod that has been detected in the last century, for example. Along with temperature gradients in different cod stocks, there is a lengthy relationship between temperature and body size. And some of the work that, for example, LND shows that look at over time, there is also changes in growth parameters of fish, decrease in maximum body size, and increase in likely growth parameter case in the North Sea for some of the fish stocks. So the questions when we started doing these modeling of fish growth and fish body size work is how would global change and particularly warming and ocean deoxygenation affect body size of marine fish in the world ocean. And we use a modeling approach to help us generate hypotheses, given our current understanding about some of these theoretical aspects of fish growth. And we know that temperature and oxygen is a first fundamental driving force of the biology of organisms, particularly the marine ectotherms that breathe through waters. The species are adapted to a particular temperature, and when temperature increases or decreases from that optimal, the aerobic performance decreases. While the decrease in oxygen also affects that aerobic performance. And that different organisms actually have adapted to different environment. As a result, they have different characteristics of these aerobic scope and temperature preference and tolerance limits. And that then affects some of the macroecological patterns, such as biogeography of the organism. At the same time, we've known for a long time that the temperature and oxygen affects fish growth as well. And one of the theory that has been proposed and that is actually used in our modeling work is the role of oxygen supply in limiting fish growth. And the central theory is that growth of fish is limited by the availability of oxygens for growth in by the fish body. And as fish grow bigger and bigger, the ability for them to obtain oxygen decrease per unit mass. In this case, as shown in this graph, the horizontal axis is the body weight, while the vertical axis is the oxygen supply per unit mass. And however, the metabolic demand for oxygen is roughly proportional to body weight because the more cells there are, the more demand for oxygen it would be. So what it means is that at some point the fish will have run into a situation where oxygen supply will just enough to meet oxygen demand. At that point, the fish will reach its maximum body size. So with that, then one can predict with increasing temperature, then the metabolic need for oxygen increase, and so the fish will run into insufficient oxygen at a smaller body size. At the same time, for example, when the environmental oxygen level decrease, so it means that the availability of oxygen decrease. And so similarly, the fish can run into problems with getting enough oxygen at a smaller body size. Consequences is that warming or deoxygenations can reduce the maximum body size of fish, and that can then have subsequent consequences on a lot of other life history characteristics, such as mortality, length or age maturity, weight maturity, size maturity, fecundity, recruitment. So based on that principle of how temperature and oxygen affects growth of fish, then we express that through a growth model. And basically, we use one of the simple growth models that were used to derive the von Bernoulli growth parameter growth model, where the growth rate is a result of the difference between anabolism and catabolism. Both of the two rate components, metabolic components, scale with body weight with different exponents, D and B. So the exponents of D for anabolism is assumed to be relates to the constraint on oxygen supply, and while in the simplest case, we assume that, for example, catabolism is proportional to body weight. So B is equal to 1, for example. So in that simplified or reduce the amount of parameters that we would need to derive the equation. And then in order to express these simple growth models and link as a function of temperature and oxygen. In this case, anabolisms, besides dependence on temperature through a Henry's equation with an exponents of J and temperature T, it is also relates to the ambient oxygen concentrations, as well as the aerobic scope G, while the catabolisms it also relates to because temperature and from there one can then derive, for example, the two important parameters for the asymptotic growth of the von Bernoulli growth function, which is the K and the asymptotic rate parameter. So I won't go into details about the derivations of that. You can refer to the couple of papers that we published. That I also put online there a more detailed example of how we can use that models to estimate change in growth under change in temperature. So by applying here, I just show some of the results when we apply the models to a large number of fish. So this is more of a theoretical analysis, idealized analysis, their current ambient temperature for each of the species and the predicted change in maximum body weight based on the equation that I just showed you. So for example, with around a degree of warming, you may see around 10–15% decrease in maximum body weight. And the magnitude of these changes actually are quite consistent with some of the changes that have been reported in the literature that are suggested to be related to temperature, such as those in the North Sea, as in some of the study that Alan and Terrace did, as well as, for example, in the Mediterranean area. And there has been meta-analysis of the effects of warming on body size across a wide variety of different organisms. For example, one of the meta-analysis is by Foster in a few years ago. And in this particular case, we extracted those organisms that are aquatic ectotherms, many zooplanktons, aquatic invertebrates. There are a few amphibians, but very few small finfish. And they found a relationship between body mass and the sensitivities of the change in body mass under warming. So in this case, the bigger the more body mass, the bigger is the degree of change in body size. And when we extrapolate that relationship to the range of body size that are common for commercial fishing, then the magnitude can reach around 10% or more per unit increase in ambient temperature. So that shows that the projected range of decrease in body mass that from a model is not totally unrealistic. And when we try to compare the predicted growth parameters with those that are observed, we find that in general, the patterns, it can mimic patterns that we see from the wild population. So for example, in this figure, the upper panel represents the model predicted growth parameter K and the asymptotic length, while the lower graph are those from fish base. So those are a large number of species, over 2,000 species of fish. And we also can roughly reproduce the intra-species variations between the growth parameters. For example, as highlighted by the black line, black dots there, or the black circle highlighted data points, which is an example for Atlantic cod. So if we just highlight, extracted out Atlantic cod, as well as the haddock in the lower case, what we find is that actually our model's predicted temperature sensitivity is slightly lower than what we observe in the case of the cod, the natural gradient across different populations of cod that with different temperature and the maximum body size. So in this case, the black dots represent the prediction from our models, while the open dots are the observed maximum body size across different populations of cod. And that lower one is basically extracted from Alan's paper for haddock. Again, we show actually a slightly a lower sensitivity of our model predictions relative to what has been observed from the time series data. So we suggested that not only that our model predictions are within the range the realistic range that can be observed in experiments, it may probably be an underestimation of the sensitivities relative to some of these, relative to the observed data in some of these wild populations of fish. So recently, I'm sure you all are aware of some debates about the use of our the oxygen limitation theories in predicting changes in body size of fish in the literature. And one of the aspects that are being debated is the use of the body mass exponent in a growth model. When we use the exponents of 0.7 in our original studies, which was also used by Formula-3, or close to the one that is used by Formula-3 when he first published the growth model. So it was assumed to be 0.7, which was kind of the average across a range of fish populations. Some fish populations will have lower exponents, while some will have higher, such as tunas and some of the pelagic sharks. So what we then did is we acknowledged that, okay, this is a simplification, so we try to test the sensitivity of different exponents in our model. And what we find actually is that for example, in one analysis, we assume a size-dependent exponent. So bigger fish, we assume that they have bigger exponent, or bigger and more active fish has a higher exponent, as observed in some of the more active pelagic fish, such as tuna and some of the pelagic sharks, while kind of inactive demersal or banker fish will have a lower exponent. And we apply that to our models. And what we actually find is that it increased the sensitivities of our models to decreasing body size under warming. And one of the reasons is that for more active bigger fish, such as tuna, although they have a bigger size exponent, but the reason for them to have such a big size exponent is that they rely on lots of energy to support their active lifestyle, to find food and to live in the pelagic environment. So it also means that they are much more sensitive to decreasing oxygen. For example, some of the tuna species cannot stop swimming because they need to keep swimming to fresh their gills with oxygen. So it means that a decrease in oxygen, for example, or increase in temperatures will have a substantial impact on their biology. And that has been observed that in the wild population, for example, for tunas, where the data shows that they are really sensitive to changes in temperature and oxygen. And so with the changes in body size and growth parameters, it may also mean that there is a reduction in growth performance. So we use one of the previous suggested metrics or indicators for growth performance as suggested by Dan Pauly, which express growth performance as a function of growth parameter K and the asymptotic rate, and that's based on basically the relationship or the trade-off between K and W infinity. So if we calculate that for one species and then try to see how that growth performance would change over time. So when we apply to cod, and then particularly we use projections of environmental temperatures by the global ocean models and apply it to the distribution range of cod, and then see how that would affect their growth performance. What we find is that our models predict a decrease in their growth performance over time because of the changes, these effects of decrease in of changes in temperature and oxygens on the growth of the cod populations. Okay. Yeah, so that's kind of basically in this case the model simulates a decrease in maximum body size and increase in K, but then the actual results is a decrease in that index of growth performance. And that relates to kind of, yeah, as I said, the plot between K and W infinity. With the changes in body size and growth parameter K, it also means a decrease. It can also mean a decrease in the population dynamics and in relation to that some of the effects on things like the productivity of the fish stocks, surface protection. In this case, for example, we look at the effects on the two temperature scenarios under the business as usual for the environment that cod are living in, and this is the predicted biomass per recruit over the different body size range. So it shows a substantial decrease in biomass per recruit by 2050 relative to 2000 period under the business as usual scenario. And this will also have other aspects of affect other aspects of population dynamics, such as recruitment, spawning stock biomass per recruit, and the relative abundance size as well. And one of the things that we need to note is often the information from that we got about how species will respond to temperature obtained from experiments, but then we need to take those experimental results in the context of the environment that species are living in, particularly in wild habitats and ecosystems. In this schematic diagram, it shows that basically in the wild populations, organisms are experiencing fluctuating environment. So there was time that the metabolic rates will be higher or lower because of temperature, and that's that determine integrations of that over time actually determine the survivorship, the growth, overall growth, and reproduction, and the ability of doing reproductive investment for the organism. But the shift in this biological rate because of warming or deoxygenation, it really changes for example, the frequency of the time that the environments become stressful and may be exposed to dangerous conditions, and thus really shifting their survival rate and growth rates. So the whole message of this schematic diagram is that sometimes the experimental results can be useful in indicating some of the response, but then really where we need to look at it from a much longer time frame and integrate that to the natural environment to really understand the implications of these changes on the marine organisms. And one aspect of that is, for example, integrating both the shift in biogeography of the organism as well as the the changes in the growth of the organism. So we hypothesized that, for example, marine species will shift their distribution range under warming to high latitude regions, and for demersal fish, it will go to deeper water. While at the same time, the populations exposing to given temperature or oxygen level will also respond by changing their body size as well. That's at the end, that interact with the need to shift their biogeography, and that would then emerge out to affect the future size distributions and biogeography of the organism, of the population, of the species of sandfish in different ocean basins. So we try to do those kind of integrations using a spatially explicit population dynamic models that we developed called the dynamic bioclimate envelope model. So I won't go into this modeling framework in detail. So basically, it link or incorporate a more mechanistic based species distribution models with spatial population dynamics, with some of the growth aspect that I just talked about, how temperature, oxygen affects anabolism, catabolism, that affects body size, growth, mortality rates, reproduction, that then affects the spatial population dynamics. So for example, with that models, we can predict the overall global distributions of across exploited fishes around the world, the sandfish body size distribution. So in this case, the map shows the mean sandfish body weight in each of the half degree by half degree pixel of the ocean. While the right-hand side shows the latitudinal zonal gradients of the sandfish body mass. So you see that latitudinal gradients, as we expected, with a smaller body size in the tropical area, bigger body size fish in the higher latitude regions. And then we used models to project the body size sandwich changes in the oceans to the future using global projection from global ocean models for the ocean variables. And this is the projected changes in the body weight of the populations across different ocean basins. So on average, it is by 2050 relative to 2000. So temperature in the oceans have increased in this time frame, and that gives us a future scenario for around approximately 1 to 1.5 degrees Celsius. So you would expect that then many populations would also decrease in body size on average around 10%, with some variations across different ocean basins. We then look at the sandwich level change in maximum body size, which basically is a result of both the effects on individual growth as well as the effects on shift in biogeography. And what we project globally is that maximum body weight is projected to increase by 14 to 24% from the 2000 period to 2050. And the changes in the temperate and tropical regions or equatorial regions seems to be in the higher range, around 20%. So with just looking there with these changes, besides being able to quantify some of the effects or of the projected effects of climate change on the body size and growth of fish, we try to then link that to trophodynamics through the body mass spectrum. So in this case, we further expand the dynamic bioclimate envelope models to incorporate the trophodynamics through a size spectrum model. So our model originally simulate changes in body mass spectrum because in our models we have body mass for individual population across different size classes, and we simulated their relative abundance. And in this further extension of the model, we then linked to the aggregate assemblage body mass spectrum, and then applied the science spectrum theory to determine basically additional constraint of thermodynamics on the availability of energy to support certain body mass within the biomass spectrum. So that's incorporated in the versions of the dynamic bioclimate envelope models called the side spectrum dynamic bioclimate envelope models. And what happens is that in some cases it does add additional constraint on the shift in distributions on some of the species. So in summary, this presentation really highlights some of the applications of some fundamental theory and assumptions about how temperature and oxygen affect growth of fish, and then using a modeling framework to generate some projections and hypotheses of how climate change will affect different aspects of body size of fish and their assemblage and how that would affect trophic. What we find is that warming the ocean nations will affect growth, body size, and consequently reductions in mortality, and that some kind of modeling applications can be used to provide some reasonable projections of climate change effects on body size of fish. There are a number of fronts that we have been doing in extension of this work. And one area of work that we have been working on is linking that to evolutionary responses, basically assuming a trait in the of fish that would be selected that affects some aspect of the metabolic performance of fish that would then have an effect on different life history characteristics and ultimately affecting fitness of the fish population, and then using that as a selection criteria to determine whether and how evolutionary responses may play a role in affecting the future changes in growth and population dynamics of fish. So thank you very much.
Okay, thank you. Thank you very much. That's a bit of a feat of endurance, and you certainly seem to be doing well. We don't want to keep you up too long, but I might invite a couple of key questions. Is that all right with you, William?
Yes, please.
Okay, so anybody key questions for William before it goes back? Tom, you can introduce yourself.
Hello, thank you for that presentation. My name is Tom Helser. I'm from NOAA Fisheries, Seattle.
Hi.
Hi, how are you? That was a very interesting talk, and in my view, sort of a theory of everything. And at the end of the talk, you talked about something very important that I think that kind of relates to most of it anyways, is that the effect of fishing pressure and size selective heritability. And so I think there's some evidence that size at age is a heritable trait, and that the fishing might have an important selective effect on that. And so I'm just wondering if you could comment whether you think that size selective fishing may alter the kind of expectations you're getting from your theoretical model relative to the observations that you compared it against?
No, I totally agree that size fission is in my opinion, the currently the largest selection force for fish is in terms of mortality rates of fish and the differential selections on killing certain types of fish or certain groups of fish with particular traits. So certainly, I think that would affect the observed. It would bias the observations that we get, particularly when we try to detect the effects of environmental change on growth and size of fish, and it also makes it really challenging for us to attribute the effects of observed changes to climate change or the changes in ocean conditions. And if we, I think that would be an interesting exercise to incorporate the size selection effects on from fishing and see how that would whether they have interactions with the effects from temperatures. I think that would be a nice exercise to do. We can look at whether there are there's additional effects, there are synergistic effects or antagonistic effects. But yeah, I agree with you. That's an important, definitely a really important factors to consider when we look at both the observational data as well as try to make projections.
Okay, it's so late there that I'm only going to ask one more question. I'm going to give that privilege to me because I'm the person with the microphone. So as you know, you were involved in our unsuccessful NERC grant to try ultimately over a longer timescale to build towards a global database of available age-length keys. What would you, if we were successful in that mission, that's a big if, but let's pretend that we would be down the road, what type of questions would you see as being available to us to answer that you would think very useful?
Yeah, so there are, I can think of a few some more applied, some more theoretical or fundamental questions. So for more applied questions, we know that we want to see how different human effects are affecting fish populations and their future viability and inform fisheries management. So in this case, it relates to the earlier questions that an important thing to know is the ability to attribute the different effects of human activities on with fish growth and body size. So in this case, that basically directly speak to the needs of collecting data, and so that we have data to then do detection and attribution studies for climate, natural changes, or fishing effects. And this also speaks to the needs of modeling work because as we discussed earlier on, because of these potential interaction between different types of factors affecting fish growth and body size, it makes it very difficult to just look at observation data and do detection and attribution. And so in this case, theoretical modeling work becomes really useful because it provides a kind of a way to generate hypotheses of what would expect in the individual effects of different factors as well as the combined effects, and then when combined with observational data, it becomes a really powerful tool to do detection and attribution. And then, so that's I think it's kind of this whole set of questions and that can be answered for that more applied side for looking at more conservations, time adaptation, that type of questions. And there's also the more fundamental questions of understanding what affects fish growth, what environment, what kind of factors affect fish growth and body size, and that also relates to, for example, some of the debate that myself and some colleagues are engaged in debating what mechanism, what factors are determining or affecting fish growth and the role of, for example, temperature and oxygen and how they affect those aspects of fish biology. And so I think, again, developing a database, combining that with models becomes really powerful tools to test, to formulate and test some of those hypotheses.